Hi, everybody. Thank you so much for coming today. I'm excited to present our speaker today, Dr. Stephen Elardo, who's an assistant professor at the University of Florida down in Gainesville, which is not too far from us. He is a petrologist and geochemist whose research mostly focuses on studying the origins and evolution of the crust of planetary bodies. Today, he's going to be specifically talking about some of his research related to our moon. He got his bachelor's degree in geosciences from Stony Brook University in Long Island in New York, and then a master's and PhD in Earth and Planetary Sciences from the University of New Mexico. And then after that, he did a postdoc at our Carnegie Institute up in DC, where he a choice. And then again, as I said, he's now an assistant professor down at University of Florida. I've known Steve for a while, mainly because I work with his wife, Dr. Amy Williams, and I was really excited now that I'm doing some research on the moon to invite him here to talk about some of his lunar research. And so thanks again for coming in person, and I'll leave the floor to you and maybe hide some of these.
Happy to be here. Thank you, Francis.
Yeah.
Great. Let's see if we can get rid
Figure it out.
There. Awesome. All right. So yeah, thank you all for coming here today. I am a moon nerd. I hope some of you are also moon nerds like I am. As Francis says, I'm a petrologist and a geochemist, so I like looking at moon rocks. I also like creating my own rocks in my experimental lab when nature does not provide me with a sufficiently high number of rocks, or the right rocks that I need to answer a particular question. So what I'm going to talk about today is the moon's near-side hot plate, or hot spot, it's been called in the literature. And I think you'll get a better sense of what that is here in a moment. Now, how many of you have seen the far side of the moon? You? Oh, really? In person? Oh, just pictures. Okay, I was like, whoa, something happened that I don't quite know about. If you were able to see the far side from Earth, which obviously you cannot, you would know that the moon is very asymmetric. It's asymmetric in a number of different ways. I'm going to discuss those ways here in a moment, but these asymmetries are some of the most fundamental and defining features of the moon itself. And I think some of the most interesting features on a planet scale in the solar system. So how is the moon asymmetric? So we're going to talk about a number of different ways. So this is lunar topography, which is a very analogous to crustal thickness. This is the near side of the moon. So this is what you see when you go up and look at the night sky, minus the pretty colors. Here is the far side. The far side crust is about twice as thick as the near side crust, with the exception of this impact basin, which is South Pole Aiken here. You also see that the near side is a lot smoother, flatter, younger. And that's because 97% of the erupted lava flows on the moon are on the Earth-facing side. When you look up at the night sky, this is generally what you see. The bright regions down here, these are highlands crust. This is primary flotation crust from the lunar magma ocean, very old. The darker gray areas, these are basically flood basalts. They cover a decent area of the lunar near side. On the far side, very, very little. So we see that fundamental asymmetry. Now, the asymmetry that I'm going to focus on today is primarily related to geochemistry. This is a thorium map from the Lunar Prospector mission, and it shows in hot and cold colors the amount of thorium in parts per million. The near side has this high concentration of thorium in what we term the Procellarum creep terrain. If you don't know what creep is, I'll explain that in just a moment. Thorium is a part of the creep reservoir. And we see that thorium is very much enriched on the near side, not so much on the far side. So these are three really fundamental, interestingly, Earth-referenced asymmetries that are on the moon. So what does that thorium enrichment mean? What exactly is it? Why do we care about thorium? For that, we need to go back and take a step back to the differentiation of the moon. And that's through the lunar magma ocean. The magma oceans have now become the paradigm for how terrestrial planets differentiate. And the moon was the model case. This model was developed in the early 70s after the return of the Apollo samples. But it posits that after the moon forming giant impact, the moon was in a completely molten state, a body of magma floating around in space. That body's going to start cooling off very quickly as it radiates heat to space. And kind of like a layered mafic intrusion for any of you that have taken a petrology class, we have settling out of dense minerals. The first mineral is olivine. It starts to build up the mantle. Heat's being lost through space. There's really complex turbulent convection. We start crystallizing pyroxene. We build up more and more of the mantle. Eventually, plagioclase feldspar starts to crystallize later on. That is interestingly less dense than the magma. So much like ice in water, the solid floats to the surface and forms a coherent crust. And this term that I've mentioned a couple of times, creep, is that last little liquid that forms at the very end of magma ocean crystallization. So it's not a reservoir that's a little sus, not that kind of creep. It is this acronym, potassium, rare earth elements, and phosphorus. Those are all incompatible elements in magmas. They prefer to stay in the liquid rather than go into a mineral. So they all get very much concentrated in the last residual liquid. Guess what? Thorium is also an incompatible trace element. So it will get concentrated in the creep reservoir. So that is the expression of what we are seeing on the near side. Is this creep reservoir that has been concentrated and distilled basically by magma ocean crystallization, the last liquid left over after the end of crystallization. So things like the rare earth elements, large ion lithophile elements, high field strength elements, and then the radioactive elements, potassium, thorium, and uranium are all concentrated in creep. And they also have very radiogenic strontium, neodymium, and hafnium isotopic compositions, very geochemically enriched. All right, but what actually is it, right? I told you it's this last stage liquid, but what is it? We don't actually have a hand sample of creep. We don't have a rock that says that is the liquid that crystallized from the magma ocean. What we see it as is a component in some lunar rocks. So it's been mixed into other types of rocks. So we find it primarily expressed on the surface as impact melt breccias. It's a component in impact melt breccias like Apollo 14 breccia 14310. And many of these impact breccias are ultimately sourced from the Imbrium Basin, which is the youngest near-side basin on the moon. So this is Imbrium. You see the high thorium areas generally surround that. That's thorium-rich Imbrium ejecta. And that rock, 14310, came from Apollo 14, which landed right about there. So interestingly, despite the correlation, which you can kind of see on those two images right there, between where creep is and between where basalts are, most Mare basalts collected from the Apollo and Luna missions are not particularly creep rich. This component resides in different types of rocks, which is kind of interesting because there's a correlation between those two, right? Why are the basalts not creep rich if we're looking at the surface and the surface is creep rich? That's kind of interesting. Okay, there's a lot we still do not know about this enrichment of heat producing elements on the lunar near side and what it means for the moon. The big question is, what is the ultimate source of these asymmetries? And that is still very much an unanswered question in lunar science. There are some models, I find pretty much all of them to be lacking in some way in explaining the asymmetries. So that's obviously the big question. I'm not going to answer that today. But why is creep dominantly found on the near side? We don't know. Where physically is it? We see creep expressed on the surface, but is that all of it? Is there still some left at the crust mantle interface? Did it get mixed into the deep mantle via convection as the mantle convects after the magma ocean stage, or is it staying at the crust mantle boundary where it can be excavated by impacts like Imbrium? We still don't really know the answer to that. That's going to be a pretty fundamental question in the rest of the talk. And then why aren't most Mare basalts creepy, right? If there's this correlation between where the basalts are and where we see creep on the surface, why are the basalts, why do most of them anyway not have this creep component in there? So these are some of the many unanswered questions related to the moon and the Creep Reservoir that I'll be touching on in the rest of the talk. Okay, everybody with me on Creep so far? Yeah? Okay, awesome. All right, so some of the driving questions for the work that I've been doing over the past few years are related to the Procellarum creep terrain. That's what I mean by this lunar hot plate, right? Potassium, thorium, and uranium are enriched in this reservoir, and they're going to kick off a lot of heat when they are concentrated to such high abundances. So how is this terrain connected to lunar magmatism? It clearly is, but not in a simple, straightforward way. So I'm going to tackle this through two different eras of magmatism on the moon. The first is the first episode of post-lunar magma ocean crust building. The first magmas that the moon is making after it differentiates into a core mantle and crust. So this is one of those rocks right there. We're going to talk about that in a little while. Did creep drive that magmatism, or was this magmatic event global? Right? That's a fundamental unanswered question that we don't know the answer to yet. And then we're going to zoom forward in time and talk about how creep affected prolonged lunar magmatism. And what do the youngest igneous samples that we currently have from the moon, what do they have to say about this story, how the moon makes magma, and what the effects are of this concentration of heat-producing elements on lunar magmatism? Okay, so let's go back about 4.35 billion years in lunar history and talk about the Magnesian suite, or MG suite for short. So this is a series of about 4.35-ish billion-year-old crustal plutonic rocks on the moon. So these are cumulate rocks that formed when a magma from the moon's interior ponded inside the crust and slowly cooled into a bunch of layers. That likely formed layered intrusions, very much like, say, the Skarsgård complex on Earth, where you have a really nice fractional crystallization sequence, where you have ultramafics like dunites and troctolites, and you have pyroxene-rich norites, then you have clinopyroxene-rich gabbronorites. This is the sequence of rocks that you get out of slow cooling of a mafic magma with a high plagioclase component. So nothing particularly shocking about those types of rocks being associated with one another. What is interesting is their geochemistry. They look like they came from very primitive mantle melts. When I mean primitive, I mean very Mg rich. So incorporating really high Mg numbers in the low 90s, like the very first types of things that would come out of a primitive mantle melt. That is also associated with an extremely high abundance of incompatible trace elements. That and their isotopic compositions link the origin of these rocks to the creep reservoir. So on one hand, we have rocks that look like they are crystallized from the most primitive of primitive mantle melts, and they have trace element compositions that look more like terrestrial granites. Those are typically not features that are found in almost any body that I know of on Earth. And here's an example, troctolite number 76535, collected from Apollo 17. That's probably the most studied individual sample from, partly because of these really interesting elements. So we're going to take a look at what role creep has or doesn't have in forming these rocks, which represent, again, that first episode of post-magma ocean magmatism. Okay, so what is probably the best model for explaining these rocks, best in part because it comes from me, is this model of mantle overturn in source region hybridization. So what does that mean? So at the end of magma ocean crystallization, we think we have an anorthositic crust, that creep layer that you've heard so much about recently, and iron-rich dense cumulates on top of the mantle, Mg-rich hot, less dense cumulates at the bottom. This is not stable in a gravitational field, and so it starts to convect. This hot, less dense stuff comes up, iron-rich, less dense stuff goes down, and you have these pods really elegantly sketched here. They come up and interact with the crustal anorthosite and this creep layer. And so you form a magma source region, right? The rock that melts to make Mg sweet magmas with these three components. Your mantle dunites give you that high Mg number. Your crustal anorthosite gives you a magma that's saturated in plagioclase, right? Anorthosite is dominantly plagioclase. And then the creep reservoir gives you those granite-like trace element compositions. So we need planetary scale processes to form these types of magmas. But a question that's been kind of gnawing at the community for a while is this a global process? Does this happen on the far side where we don't have creep? Or is this localized to the near side? So basically, is creep a passenger or a driver in this type of magmatic event? Okay, so the MG suite samples from Apollo, the Apollo missions are ubiquitously creepy magmas. They have incompatible trace element abundances represented here by the rare earth elements in excess of 300 to 1,000 times chondrite. So this is a plot of the rare earth element abundance over CI chondrite. These are the rare earth elements here. So this is just chondrite normalized abundances. This dark black line here is our model for the creep composition itself. And the red and the blue fields are estimated parental magmas for the MG suite. So these are shockingly enriched in what looks to be a creep reservoir. So is that a bias of our sample collection because all the Apollo missions landed in and around the Procellarum creep terrain? Or is this a feature of its petrogenesis? If we look at the lunar meteorite collection, things get a little bit more interesting. Lunar meteorites, we don't know exactly where they came from on the moon, but overall they should represent a random sampling of the lunar surface. Some folks, such as Juliana Gross and co-workers, have proposed clasts like this. So this is a rock clast inside of a breccia that is a lunar meteorite. These are just two X-ray images of the same sample. She and others have proposed that they find MG suite clasts in breccias that are creep-free. That would suggest this magmatism happened all over the moon. But it is really difficult to get ages for these types of samples. And also, we don't really know where they came from on the moon. Not every rock from the near side is creepy. We don't know where this rock came from. And so it's hard to make links between little clasts that we find that are a couple of millimeters in size and a specific magmatic episode on the moon. Okay, so for this first project that I'll talk about, I approached this in a couple of ways. Trying to go after the questions of how creep affects the production of MG suite melts, and then through that, can we add constraints to the extent of early crust building magmatism on the early moon? So we're gonna go back to this model here where we have this 3-component source region for MG suite magmas, right? Where we have crustallonorthosite, these MG-rich dunites, olivine-rich rocks, and this creep layer. There are basically 2 ways that we posit that creep can affect magmatism in general. So 1, radiogenic heat leads to melting. It's got a lot of thorium, potassium, and uranium. That kicks off heat. That heat leads to a melting rock. The other way that we're proposing in this study is melting point depression, right? Creep is the last liquid formed in the magma ocean. So by definition, it has the lowest melting point out of any major lunar reservoir. So what happens if you start adding this creep component to rocks? Does it lower the melting temperature of that particular source region, leading to more melting? So I approached this in 2 ways. First, I brought in some collaborators to help out with some heat production calculations. You'll see those here in a minute. And I'm going to test model 2 first. I'm going to do that by making my own rocks through high temperature experiments to get at the effect of creep on the melting temperature of MG suite mantle sources. Okay, so how do I set up these experiments? So I need those 3 components of that source region that we talked about before. I need the mantle, I need the crust, and I need a creep component. So for the mantle, I selected these beautiful San Carlos olivines. They come from Arizona. They are MG-rich olivines, and they are excellent analogs for mantle dunites on the moon. They have about the same engine number, same mineralogy, excellent. So how then do we add the crust? So to add in the northosite crust, I obtained some of these samples here. These are megacrysts of anorthite from the Miyakijima volcano in Japan. And what's special about those is that they have an anorthite number. This is basically the ratio of calcium to calcium plus sodium plus potassium in feldspar. Point is, they are a perfect compositional analog for the lunar crust. And Miyake-Jiva anorthite is often used as a component for laboratory remote sensing studies of the moon because its composition so perfectly matches that of the lunar crust. So we can mix those two together. We combine those in 50-50 proportions. And then in my laboratory, I mix up a synthetic creep composition. This is something that's in the literature. I can take reagent grade oxides from like industrial producers in my lab, mix them together in the right proportions to make something that is chemically the same as what we think creep is. And then I take that 50-50 mixture and I add in between 0 and 50% of that synthetic creep. So chemically that will, not from a heat production standpoint, but chemically that is akin to a source region in the mantle with different amounts of creep. And we're going to do some melting experiments then to look at how creep affects the melting temperature of that anorthite olivine and anorthite source region. So these were done in a controlled atmosphere furnace towards the end of my postdoc at Carnegie, what is now the Earth and Planets Lab. So here's that furnace here. So we mixed up those components together, put them in this furnace at temperatures between 1175 and 1300 degrees C. We had redox conditions that were appropriate from the moon for lunar magmas. We used rhenium wire loops for any experimental nerds. That does not suck up iron from your melt like other metals do, so it's really great for these types of experiments. And we let them sit at that high temperature under controlled atmosphere between 4 and 6 days. That promotes equilibrium, elements diffuse, and we end up with experiments that look like this. This is a backscattered electron image from a microprobe. And the important points there, the really bright gray area, that is the liquid. That was little magma during the experiment. The really dark crystals like that one there, that's a bubble, sorry. Like that one right there, that is plagioclase. And then the intermediate gray, like that big one like there, that is olivine. And so we can measure the composition of the melt, we can measure the composition of the minerals, and make some interpretations based on the results. Okay, so here's probably the money figure for this particular study. So what are you looking at here? You're looking at a plot of melt fraction in the experiments. So basically how much liquid, how much melt is there as opposed to olivine plus plagioclase versus the amount of creep that I put into that starting composition. So there's 0, there's out to 50%. And what do we see? We see that creep has, at a particular temperature, a dramatic impact on how much melt is present in those experiments. So let's take a look at, say, the 1250 degrees Celsius series here. So in these nice pink colors. So at 1250 C, when there is no creep in that source region, you get about 8-9% partial melt. When there's 25% creep, you get about 50% partial melt. So adding creep to that same mixture of olivine and plage dramatically increases the amount of melt that that source can make at a given temperature. So what we find is that at conditions that produce troctolite parental melts, the troctolite rocks, olivine plus plagioclase, like the image that I showed you of that like baseball-sized rock from Apollo 17, at conditions that produce those types of rocks, creep can result in about 4 to 13 times more melt production over situations, rocks that have no creep, that are far side and analogous. But what about the compositions of the melts? All right, fine, Steve, you made more melt, but is it the right composition of melt? Do we have, say, Mg numbers in those melts that make those really high Mg numbers that are so characteristic in the minerals in these rocks? So we can match that as well. So this is just simply Mg number of the olivines in the experiments. The Mg number is just magnesium over magnesium plus iron times 100, right? So here is the range in gray here for Mg's sweet troctolites. So the olivine in those rocks. And the dots are the Mg numbers of the olivine in my experiments. Most of them fall within this range. And the ones that are high are relatively easy to explain. A little bit of fractional crystallization will drive the Mg number down into this range. So it would have been very problematic if we had put 50% creep into these source regions and got MG numbers in the 70s off the screen down here. That would have been like, it deals off, right? That does not work. But within this field or a little bit higher, we're matching those parental melts really, really nicely. So what about radiogenic heat? What contribution does that have? So I brought in a collaborator, Matthew Lanoville, whose work will come up a little bit more later in the talk. And he conducted some heat production calculations. So what he did was he took the same source regions that we had, so creep-bearing Mg suite sources located at the base of the crust or the upper mantle, and did heat production calculations. So given the abundance of the radioactive isotopes at about 4.35 billion years ago, how much heat are they kicking off in a relative sense, right? Do those source regions, that source region at the base of the crust and the upper mantle, does it heat up or does it cool down, right? Because the moon's also losing heat through its crust to space. And so he varied the amount of creep in the source regions the same way we did, in his case numerically, from 0 to 50%. And he used a range of cooling rates for the lower crustal environment at about 4.35 billion years ago in the moon. And these are derived from his global 3D thermal evolution models. And so we took basically the entire plausible range of cooling rates for the lower crustal environment and calculated what the relative heating or cooling would be of those source regions. And this is just a really sweet picture of plutonium glowing from the Department of Energy. I love that. Looks like tasty, like it would taste like orange or something. Gummy, but it's really spicy. I don't. I hope it's like a big chunk. That would be really good. Okay, so let's take a look at some results of those calculations. So what are you seeing here? You're looking at cooling rate. This is basically the whole range of possible cooling rates from his models for the lower crustal environment versus the amount of creep in a hypothetical source region. The color scale on here is simply a delta T, a change in temperature in that rock as a function of amount of creep and the cooling rate. Here is basically the point in which heating and cooling balance out perfectly, where you get no change in the temperature of that source region. But what you can see is that from low cooling rates, the source starts to heat up with just a little bit of creep, right? And this is basically change in degrees per million years. And even at the highest cooling rates, any source region with about 20 or 25% creep results in heating. That source region will heat over time, just due to the radioactivity of those elements. That will also contribute to the amount of melting that you get from that source region. And that is not occurring on the far side where we do not see the creep reservoir expressed. So basically what we can say is that both directly and indirectly through either melting point direct depression or direct radiogenic heating, creep is heating the mantle up, and it is should produce, we estimate, between 4 and 13 times more Mg sweet magmatism on the lunar near side. And that number is without any input from radiogenic heating. So it doesn't mean that there can't be far side Mg sweet rocks, but if there are, there should be a hell of a lot more on the near side. So this is a magmatic event that we think is biased towards the near side because of the creep reservoir being present there. Okay, so let's zoom forward in time and we'll talk about the youngest sampled igneous rocks that we have from the moon. And those are the basalts that were collected by the Chang'e 5 mission in this particular region right here. So this is an image from the Chinese lander as its arm is getting ready to collect samples from the moon. All right, so quick recap on the Chang'e 5 mission. So this was China's first sample return mission to the moon. They're actually now getting ready to launch Chang'e 6, which will be a sample return mission to the South Pole Aitken Basin on the moon. So remember the far side with that really high crust, and that was that big crater at the bottom, that's South Pole Aitken. A really great target for sample return. Chang'e 5 was the first sample return mission since the Soviets last did it in 1976. And they returned about 1.73 kilograms of rocks and regolith in December 2020. So here are the sites for the Apollo missions. And then there is the landing site for Chang'e 5. This is Oceanus Procellarum. Over here, you'll get a better look at that in a moment. And there is the Chang'e 5 landing site. So it is sort of on the outskirts of the, at least surface expression of creep. So there's the Imbrium Basin. I showed you that earlier. I've rotated the moon slightly in its perspective. And there is the Chang'e 5 landing site. It is in a young Mare volcanic flow, sort of in between the Mons Rumker volcanic complex and Myron crater. You can see in thorium, Myron crater is a big hotspot. In thorium, you can see it also on the global map right there. And so they landed on what turned out to be, after radiometric dating, a 2 billion year old volcanic flow on the moon. And that's really interesting, especially to people like me who think about how magmas are produced in the lunar interior, because that is a full billion years younger than any other igneous sample that we had on the moon. So gives us a window into the magmatic evolution that we did not have before. Now this region, the whole region, is adjacent to really thorium-rich Imbrium ejecta, and magmatism in Oceanus Procellarum more broadly spans at least 2 billion years. So this is really indicative of the long-lived production of mantle-derived melts, and we can tell from remote sensing from heterogeneous sources. So different types of mantle rocks are melting over at least 2 billion years to produce magmas in this region. I am really interested in why that is the case and what connection the creep reservoir has to that magmatism. So let's look in the Chang'e 5 samples a little bit more, because we have a sample, we can do detailed geochemistry on it. So the Chang'e 5 samples. Here is another chondrite normalized rare earth element pattern, a set of rare earth element patterns. So here's the Chang'e 5 sample in these red dots. That is the rare earth element pattern of the basalt itself. In gray down here are a selection of representative rare earth element patterns from other different basalt types on the moon. They are all less enriched in rare earth elements than the Chang'e 5 samples. And then here is an Apollo 15 creep basalt. Pretty similar, right? In shape, pretty similar in shape. The light rare earth elements over here are enriched. It has a negative slope, big negative europium anomaly. Looks a lot like creep. So should I take bets? Is this a creep-rich sample or not creep-rich sample? Hands for creep-rich. Okay. It's fine. Shout it out when you have a guess. Hands for not creep-rich. Okay. If I'm asking, I'm probably going to surprise you with the next slide, right? Okay. So rare earth elements are fine. They're really useful. In almost all of geochemistry, isotopes, especially radiogenic isotopes, are the gold standard. They give you far more detailed information about rocks than elemental abundances do. All right, so what are we looking at here? We are looking at what's called the TI diagram. So this is time versus the initial isotopic composition. In this case, the initial neodymium isotopic composition, resulting from decay of the samarium neodymium isotopic system. And this plot right here basically shows variations in the initial neodymium isotopic composition of various lavas from the moon, from Apollo, from Chang'e, and from basaltic lunar meteorites compared to chondrites. So chondrite being that's what the bulk moon should be. That's what the solar system initial should be. So a chondrite, as it evolves through time, as radioactive decay changes its isotopic composition, will fall on a flat line, because we are normalizing data on this plot to chondrites. So also we subtract a 1 in the equation, and so you get a 0 there. So that is chondritic evolution. Creep, as a geochemically enriched reservoir, evolves along this orange line here. So this is an Apollo 17 creep-rich basalt. This is that Apollo 15 creep basalt that I showed you the rare earth element diagram on the last plot. This is a creep-rich lunar meteorite here. So creep evolves along this line with time. The Chang'e 5 basalts are way up here. They are sourced from a mantle source region that indicates long-term incompatible element depletion. Not an enrichment like the rare earth element diagram would try to trick you into believing. The isotopes are far more definitive that creep is not in the mantle source of this basalt. That is really interesting because this is a young basalt at a time when magmatism on the moon is waning. It is tailing off. We are not getting much melting in the mantle. And so excluding a major heat source from its mantle reservoir is pretty interesting. So what gives? What was the heat source for prolonged lunar magmatism? Was creep involved directly? Doesn't look like it. Was it involved indirectly? Maybe, I don't know. We'll find out. So where in the mantle did these melts come from? That is a big question. Where? Is it deep in the mantle where the planet should still be warm, much like our planet is very hot deep within the mantle? Or is it somewhere more shallow? So that is what I was interested in getting at with another set of experiments. So the goal for these experiments was to determine the pressure temperature conditions of liquidus multiple saturation to determine the origin of these magmas. If that sentence doesn't make any sense, I'll explain it in a moment. So I selected the composition of one Chang'e 5 basalt, and this was from a published paper by Tian et al. In Nature. And this sample represents, importantly, a liquid composition. So this has, this small fragment is the same composition, I believe, as the melt itself, which is really important. And it is in equilibrium with the most Mg-rich olivine reported for Chang'e 5. So that tells me this sample, it's in equilibrium with the most Mg-rich olivine. If it had undergone fractional crystallization that changed the melt composition, it would have a lower Mg number. We don't want those samples. We want the more primitive ones. Those are the ones that we use for the experiments. So that composition served as the starting point for another synthetic composition that I did piston cylinder experiments on in my laboratory at UF. And that's the piston cylinder instrument that I used to conduct this study. And we also did calculations just as kind of a gut check using the thermodynamic modeling software Perplex. Okay, so multiple saturation points. What can they tell us? So first we need to start with some assumptions. So if a mantle-derived basaltic melt, because basalts are the types of melts that we get out of mantles, if it has not changed its composition significantly since it was extracted from its source region, so imagine a mantle rock, it's heating up for whatever reason, it generates some basaltic liquid, and that liquid makes it to the surface without having significantly changed in composition in any way. And if that melt left behind 2 or more minerals in the mantle, as is extremely commonly the case on Earth, the Moon, Mars, then what you can do is you can take the composition of that melt, do experiments like I did, and put together a temperature versus pressure phase diagram. This will show you the regions where in pressure temperature space there is only melt, or there is, say, melt plus olivine, the most common mantle mineral, or melt plus pyroxene. The point in PT space where there are 2 minerals on the liquid is at the same time. Again, remember, if this melt left behind 2 or more minerals in the mantle, that tells you the pressure and temperature of melting. Pressure is obviously proportional to depth. That tells me where in the mantle this particular melt came from. And that's what I just said. The high temperature PT conditions tell you the melting conditions. So there are some assumptions, but I think that these rocks meet those assumptions. Okay. So here is the temperature pressure phase diagram that I produced for the Chang'e 5 basalts. So a couple of things to note. Remember, I said that that melt cannot have changed significantly since extraction from the source region. The 2 most likely minerals to fractionally crystallize, if say this lava had ponded in a shallow crustal magma chamber, are olivine and pyroxene. Those are the most abundant in the mantle. And so if they were fractionally crystallizing from the melt shallow, at low pressure, we should find olivine and pyroxene on the liquidus, the first minerals to crystallize. We do not. We find plagioclase and a high titanium oxide. So olivine and pyroxene don't appear within 35 degrees of the liquidus. That indicates to me that this lava probably did not undergo significant fractional crystallization since its extraction from the source region. And there are some other lines of evidence to suggest that as well. So that's the 1 bar crystallization sequence. Those were done in a similar type of apparatus as the first project. And again, that argues against extensive fractional crystallization. All right, so I think we have something that is probably approaching a primary melt, which is good, because we want that to look at the multiple saturation points. Okay, there is the inferred high pressure liquidus multiple saturation point. So what are we looking at here? In this diagram, we have this sort of tan line. That's where plagioclase crystallizes first. That's the liquidus phase. Very quickly after that, we have a high titanium oxide. Usually it's ilmenite. Then we have olivine and clinopyroxene that come in later. But you notice that all of these minerals going to higher pressure converge at the liquidus in this general region here. So we have a 4 mineral multiple saturation point somewhere around 0.4 to 0.7 GPa, gigapascals. So in the moon, that corresponds to about 75 to 130 kilometers depth in the mantle. I don't have it today, but the perplexed phase diagram, the calculated phase equilibria shows something that's almost identical. That's pretty shallow. That is not deep mantle melting. Oh, I do have the perplexed phase diagram. Here you go. It's basically the same. A complex multi-phase liquidus saturation region right around there. Same minerals, about the same conditions. It's a good gut check. Okay, so we have convergence of not 2, but 4 minerals at the multiple saturation point. We have the lack of any mafic silicates within 35 degrees, the 1 bar liquidus. In all of the Chang'e 5 papers I've seen so far, there haven't been any olivines reported that have an Mg number higher than 34. If there had been, that would tell me that the melt composition that I used was wrong. The strontium and neodymium isotopic systematics also suggest plagioclase in the source region, consistent with plagioclase at our multiple saturation point. And clinopyroxene thermal barometry on the samples themselves are consistent with clinopyroxene forming between 0 and 0.7 GPa, nothing higher than that. So consistent with crystallization of this melt starting no more than about 0.7 GPa and crystallizing as it goes to the surface. So I argue that these represent the conditions of melting for the Chang'e 5 basalts, which is really interesting because just 2 billion years ago, as magmatism was waning, we had melting of a shallow upper mantle source region. And that melt erupted without extensive fractional crystallization. Another way to get that rare earth element pattern that looks so much like creep is to basically have a very low degree partial melt. Remember, rare earth elements are incompatible. They will go into the melt as long as there is melt there. A way to artificially enrich them and make them look really, really high in that melt is to just have a little bit of it in the source region, low degree partial melting. So I think that's probably more consistent with the data. And then we also had plagioclase in the source region that comes from the isotopic systematics. And there is no evidence from the Chang'e 5 basalts that melting in the moon moved deeper with time. I say from the Chang'e 5 basalts, this is one sample, right? There are other young basalts on the moon. This needs to be assessed more broadly, but we don't see any evidence that melting moved deeper with time. Okay. So how does the moon melt so late in its history? Why isn't this region at 75 to 130 kilometers, why isn't that cold elastic lithosphere at this time? The moon's continually losing heat to space, right? Why isn't the lithosphere in this region getting really, really, really thick? Okay, this ties in, I think, the answer to Matthew Landeville's global thermal evolution models. So he did a series of 3D global convection models where he put creep artificially enriched on one side of the planet, so an asymmetric boundary condition. And what he showed is that the mantle temperature profile is highly sensitive to the physical location of creep in the nearside crust. And that is so important because anorthosite, as a type of rock, has a low thermal conductivity compared to the mantle. It's about half the thermal conductivity of mantle rocks. And so let's take a look at 2 different slices here. So these are just, slices of the moon itself through the core at different time periods. Hot colors are hot temperatures, cold colors are cold temperatures, and the white regions here correspond to where his models are making melt. So this is what the thermal evolution of the moon looks like in his models if creep is present at the surface of the moon, where it's radiating heat to space. This is where what it looks like if creep is a subcrustal layer, if it's under the anorthosite crust. Yeah, yes, the numbers are billions of years. Thank you. So right smack dab in the middle is where Chang'e 5 erupts 2 billion years ago. So surface, subcrust, surface, subcrust, big difference. A lot more melt later in lunar history just by moving the physical location of creep underneath a plagioclase crust. So I think this holds the answer to why the moon is melting in this region 2 billion years ago. So here is an image of the Chang'e 5 landing region, northern Oceanus Procellarum. There's the site itself. There's Myron Crater. You remember that creep ridge hotspot there. And this is sort of my cartoon diagram, or my buddy likes to call these geophantasmograms of what I think is going on underneath Oceanus Procellarum. So you have that creep-rich Imbrium ejecta layer here that's all over the near side. You have an anorthosite crust, and you probably have a discontinuous but subcrustal layer of that original magma ocean liquid that has still survived at least to 2 billion years ago. It is conductively heating the mantle, right? It's kicking out heat because of the potassium, thorium, and uranium. And so you have top-down conductive heating of the mantle and less heat moving through the crust due to the differences in thermal conductivity between crustal rocks and mantle rocks. More heat gets transferred to the mantle in this situation. And so I believe that top-down heating of the mantle basically promotes long-lived lunar magmatism on the near side. Okay, so just to summarize for the talk, how is the moon's near side hot plate, that PKT, how is that connected to lunar magmatism? Well, we think we've got at least some answers now. It's both directly and indirectly. It can do it through melting point depression by changing the melting point of a rock, direct heating leading to melting in the case of the MG suite, and then indirect heating of the mantle throughout lunar history. So is that first episode of crust building, is it global? Or did creep drive that magmatism? Well, it could be global, but even if it is, we should expect to see significantly more of that crust building magmatism on the near side, even without any input from radiogenic heat, just from the melting point depression aspect. And then lastly, how did the PKT effect prolong the lunar magmatism? I think it affected it in a big way. And I think that the 2 billion year old Chang'e 5 basalts likely came from low degree partial melting of that shallow mantle source region that was kept hot for long periods of time from top down heating from a subcrustal creep layer. So I think hopefully this really emphasizes the incredibly important role that these asymmetries on the moon have had on its geologic evolution throughout lunar history. Thank you very much.